Hi, I'm Ed Rutherford. I'm a fisheries biologist at NOAA Great Lakes Lab, and I'm going to be talking to you about tipping points for coastal food webs. In the Great Lakes, we've seen two trends happen over the last 10 to 20 years. In nearshore areas, we've seen increases in harmful algal blooms, as shown in the image on the left. That's a harmful algal bloom captured in Lake Erie during the summertime. And then also in the offshore zone of the Great Lakes, we've seen a decline in biomass of fish in particular. And another factor to consider in all of this is the role of invasive species, in particular the zebra and the quagga mussels, which have changed the cycling of nutrients in the nearshore zone, increasing harmful algal blooms, but decreasing the availability of nutrients to the offshore zone, resulting in a decline in fish production and harvest. So for tipping points, we're going to focus on three watersheds and nearshore food webs: Saginaw River watershed and Saginaw Bay, Maumee River and western Lake Erie, and the Fox River and Green Bay. And the tool that we're going to use to translate the changes in nutrient loads coming off the watershed and how they affect the coastal food webs is a well-known food web model developed by scientists at University of British Columbia to look at nutrient and fisheries harvest impacts on food webs. It's called the Ecopath with EcoSim model, and we've adopted it for use in the Great Lakes. The driving force in this model is the amount of nutrients coming into the food web. And as you can see here, this is a snapshot of a food web and the model works in two ways. You first configure the relationships and the biomass of organisms in the food web and define who's feeding on whom. And then once you've set that, you can run the model forward in time and look at the various scenarios of increased or decreased nutrients or increased or decreased fisheries pressure. So we developed a model, and an example I'll talk about today is for Saginaw Bay. And it's a model that my colleagues Yu-Jun Kao, Sarah Adlerstein, and I worked on, published in 2014. We calibrated the model for an earlier time period in Saginaw Bay, the late 1980s, early 1990s, and ran it forward in time up near to the present, to 2009. And then we ran a number of scenarios of various nutrient loads coming from the Saginaw River watershed to see how the food web would respond to changes in nutrients. And here's the types of results that we get out from such a model. And shown are four taxa of interest to stakeholders. Cyanobacteria, shown in the dotted blue line, is a blue-green algae known to cause harmful algal blooms. The red line is adult walleye biomass. The green line is Cladophora, which is responsible for much of the muck that washes up on beaches in Saginaw Bay. And the dashed green line is adult yellow perch. The red arrow indicates the current level of nutrient loads in Saginaw Bay as best as can be estimated. So notice that different taxa in the food web respond differently to increases in nutrient loads. You can see that walleye and cyanobacteria, or the blue-greens, that cause harmful algal blooms keep increasing in biomass as we increase nutrient loads, whereas yellow perch and Cladophora pretty much reach a peak at the current level of nutrient loads coming into the bay. And this has implications for management. If we decide to reduce or increase the nutrient loads, we will sacrifice biomass of yellow perch at the expense of increasing both harmful algal blooms and walleye biomass. So that's an example for Saginaw Bay. We know that in western Lake Erie, we have serious harmful algal blooms, and on the left you can see a satellite image of a enormous harmful algal bloom during the summer of, I believe, 2011. And when the algae bloom and are dispersed throughout the lake, they end up settling in the central basin of Lake Erie and sink and cause hypoxia, or low oxygen conditions at the bottom of the water column. And this forces a change in the distribution of organisms in the food web, as shown in this slide. The top slide depicts where organisms are in time and space when there are high oxygen conditions, when the water is well oxygenated. And the lower graph indicates what happens when there's hypoxic conditions in the summertime. Notice that fish are distributed up in the water column and near the bottom when there's plenty of oxygen, but when there is a hypoxic condition in the bottom waters, it forces some organisms off the bottom and makes them actually more vulnerable to predation by key predators like walleye. So we think that this may have long-term consequences for the structure and the health of the food web. To just illustrate some of the predictions that our models can generate, they are listed here. It ranges from the predicting biomass of blue-green algae or Cladophora, which causes the muck on the beaches, various members of the food web, including the fish species that we're showing here. The information gained from this exercise is useful for improving water quality, especially in the coastal zone, because it allows the stakeholder to understand how much nutrients is coming down and entering the coastal zone food web and stimulating the growth of harmful algal blooms, blue-green algae in particular, and also the growth of nuisance macrophytes, which are plants like Cladophora that grow in shallow nearshore zones, die, and end up as muck on the beaches, reducing property values.